Hello everyone! In this video we will continue to examine topic 5.4, the magnetic effects of electric currents, and in particular we will begin to discuss the force on a current carrying wire. Alright, so big picture, right? Huge conceptual structure. We've discussed how moving charges or currents produce magnetic fields. We introduced our right-hand rule as a way of deciding what direction those fields were in, and we said those fields were concentric circles, okay, with strength, field strength given by B equals mu over 2 pi I divided by R. But it is also the case that magnetic fields interact with moving charges and produce a force on them. So moving charges produce magnetic fields, but those magnetic fields interact with other moving charges and produce a magnetic force on them. Notice this has exactly the same structure as for example, electric force and field and gravitational force and field. With electric force and field, charges produce electric fields, and then those fields act on other charges to produce a force on them. Same dynamic here, except the thing that is producing the field is moving charges, and that moving is non-optional. So it's moving charges which produce magnetic fields, and those fields interact themselves with other moving charges. So consider a current carrying wire in an external magnetic field. That is, here's my current carrying wire. It is carrying current to the right. It is of length L, or there is L inside the field, and B external is applied. Notice this is not the field. The green B field is not the field that is being produced by this current carrying wire. That would look like this and would obey the right-hand rule we have already learned. Instead, this is an external field from, let's say, another wire or a horseshoe magnet or some other source of field. Forget where it comes from for now. And the point is that the current carrying wire inside that field will feel a force. It experiences a magnetic force that is perpendicular to the current itself, and in fact is also perpendicular to the magnetic field. This is unlike any other force law we've ever seen. When the current is to the right and the field, the external field, is inwards, it experiences a force up the page here. Notice that that is perpendicular to the current, and it's harder to draw, and it's perpendicular to the magnetic field itself. The magnetic field is into the board here, and that force is up. And so that's a 90-degree angle as well. And the size of that magnetic force is given by this particular force law. This is FB is equal to ILB sine theta. This is the magnetic force on a current carrying wire. And we'll unpack this a little bit term by term. So that first ingredient here is the magnetic force on that wire is proportional to the current. Okay, seems pretty straightforward. It is also proportional to the length of the wire, right? The amount of the wire that is within the magnetic field itself. Okay, so how much of the wire is actually within the field? That's L. It is also proportional to the external field strength, which is not terribly surprising. So if you double the field strength, you double the magnetic force. And then there's a term, sine theta here, where theta is the angle between the magnetic field and the current. And we're going to explain this in a little more detail in just a bit. But the key idea is that theta here, right, if theta is 90 degrees, then you get a maximum force. So the maximum magnetic force is when the current and the magnetic field are exactly at right angles. If they're not perfectly at right angles, you will get a weaker force than would be possible if it were at right angles. You can think of this term as sort of how much of the magnetic field is perpendicular to the current. That's a good way to interpret that B sine theta term there. And finally, you get the direction of that magnetic force from a new right-hand rule. Now, it's important to note that there are lots of different right-hand rules, and even I think the book discusses Fleming's left-hand rule for this particular force law. I will say I have my preference, and I'm going to teach it. I don't mind which one you use. There's no problem there. But I'm going to be super consistent with a particular right-hand rule that differs from the one in the book. And I'll explain a little why I prefer this one in just a moment. So just for those HL mathers following along, this ILB sine theta should jump out at you just a little bit. We are secretly sneaking in not a dot product, but a cross product. And that is fundamentally what is going on. IL cross B is equal to the magnetic force. If you don't know what I'm talking about, that's totally fine. That's not a problem. I just wanted to point it out for those who had seen cross products in HL math. That is what we're doing with this particular force law. The right-hand rule that I am going to use and to teach in this course is one that has the current in the same direction as your thumb. And this is so that your current is always the thumb. That's why I like this particular right-hand rule. So for both the right-hand rule used to find the field produced by the moving charges and this right-hand rule, which is used to find the direction of the force on those moving charges, the thumb is in the direction of the current. So in this example, your thumb is pointed in the direction of the current. Then you use your pointer or index finger to point in the direction of the magnetic field. So thumb in the direction of the current, pointer or index finger of your right hand in the direction of the external magnetic field. Then finally, what you get is your magnetic force is in the direction of your middle finger, right? Crooked out, right? Bent right at the second joint so that it points away from the rest of your hand. So if your thumb is in the direction of the current, your pointer finger is in the direction of the external magnetic field, okay? Then your middle finger of your right hand will determine the direction of the magnetic force. Notice that it is at right angles to both the current and the external magnetic field. So using this right-hand rule, we can apply it to other orientations, including what happens if the current is straight up and the magnetic field is out. Well, if the current is straight up, you put your thumb in the direction of the current, you point your index finger in the direction of the magnetic field straight out, and that gives you a magnetic force to the right. You'll notice you may need to sort of break your wrist to do this fully, but that's just part of the deal. And I would encourage you to sort of practice along with each of these sort of different orientations as we move forward. So what about this example? Well, the current is up the page, the magnetic field is to the right, and therefore that magnetic force can be represented using arrow notation into the board. So it's going to push this wire into the board. What about this example? Well, the current is out. Okay, the current is out. The magnetic field is down, so pointer finger down the page gives you a magnetic force to the right. And what happens if you switch the direction of that current? Well, even if you didn't reapply the right-hand rule, if you simply reverse one of the things, you will end up reversing or inverting the direction of that magnetic force. Note that in questions on these, you could be given the magnetic force and the external field and asked to find the current, or you could be given the current and the force and asked to find the external magnetic field. So you need to be comfortable in any order figuring out what the final direction would be. One final example here, if the current is going into the board and the magnetic field is pointing from north to south and this horseshoe magnet to the right, then the magnetic force felt by that wire will be downwards. It'll be pushed downwards in this particular field. Finally, we can ask one more question, which is, what if the magnetic field and the current are not perfectly perpendicular? Okay, which does happen in real life. How do we figure out what direction the force should be? If our force is given by this expression, and the right-hand rule here is assuming that, the right-hand rule assumes that these three things are perpendicular. How do we figure out what direction the force should be in? And the answer is to draw it out. So draw out your magnetic field and your current at some particular angle theta. Notice that the magnitude of that field will be reduced by this sine theta term, which we've already discussed. But to find the direction, what you want to do is think about how much of the magnetic field is perpendicular to the current. So you're going to decompose the magnetic field, perhaps in your head, and simply think about, well, of this magnetic field at an angle to I, how much is perpendicular to I? And notice that the magnitude of that magnetic field perpendicular to I has the magnitude b sine theta. That is no accident. And so what you're going to do is you're going to use this perpendicular component of the magnetic field to determine the force direction. So you put your thumb in the direction of the current, you put your index finger in the direction of the perpendicular component of the magnetic field, and that gives you a force direction out in this particular situation. So the magnetic force would be out on this particular wire. Note that the resultant magnetic force is perpendicular to both IL and that perpendicular component of the magnetic field, although it is not perfectly perpendicular necessarily. It is perpendicular to both IL and the magnetic field itself. It is pointed out in the third dimension here. Notice what happens if you have perfectly anti-parallel alignment, that is, if the current is opposite the direction of the magnetic field and not just aligned. Well, then sine of 180 is equal to 0, and that magnetic force is 0. So just as in the case if the current is directly aligned with the magnetic field, there is no perpendicular component, and therefore the magnetic force is 0 in that scenario.